numbers on a paper.
Hello dear friends, welcome to Humble Mark Academy. In this video guys, we shall be looking at the proof of the P series, namely guys the proof that if we have a series such as n equals 1 to infinity of 1 over n raised to the power p guys, this series in particular, that it converges whenever p is greater than 1 and diverges whenever p is less than or equal to 1. Great. So guys, before I get started, I want us to introduce ourselves guys. I am Omenju Macarius and this is Humble Mark Academy, where I take complex science concepts, those ones that students find it very difficult to understand. I break them down into tiny pieces such that any student across the globe can use his or her own understanding now to score a better mark in his or her exams guys. In exchange guys, all I want you to do is to hit that subscribe button looking at you, because I can only help you to pass your exam so well once you've subscribed to my channel guys. And please give the video a thumbs up. That goes a long way to motivate me to keep creating more great contents for you guys. Thank you very much. Please share the video out with your friends so they can have access to great contents like this. And friends, if there's something you understand, please let me know in the comment section down below. I'm going to get back to you explaining greater details for your understanding. Let's get started. Great guys, welcome back. All right, so guys, this is the series we are talking about, the series as n goes from 1 to infinity of 1 over n raised to the power p. So guys, let us notice that the series from n equals 1 to infinity of 1 over n raised to the power p guys, we can draw certain conclusions about this our series. We can see that first of all guys, in the very first place, we can see that the series is a positive series, that is for every n greater than or equal to 1. This our series is positive. And guys, the series as well is decreasing on the interval from 1 to infinity. Again guys, we can see that the series is continuous, that is from 1 to infinity. Great. So guys, by this now we can examine this our series now in three cases. One, the first case is going to be when p is equal to 1. The next case guys will be when p is greater than 1, and we are going to end when p is less than 1. Great. So guys, in this case, whenever p is equal to 1 guys, we can see that this our series, that is the series from n equals to 1 to infinity of 1 over n raised to the power p guys, simply becomes now the series as n goes from 1 to infinity of 1 over n. So guys, this, as you all know guys, is a famous harmonic series that diverges. Great. So guys, whenever p is equal to 1 guys, the series we all know guys is harmonic, right? It's a famous harmonic series that we all know that it diverges. So guys, as soon as this video ends, I'm going to produce the video that is going to be proving that this famous harmonic series that we all know actually diverges. Great. So guys, this is the case when p equals to 1. The series, the p series when p is equal to 1 guys, diverges. Now guys, for us to be able to prove when p is greater than 1 or when p is less than 1, we are going to be using the integral test in this case. Okay, that's the test. That's the case 2 when our p is greater than 1. We are going to be using the integral test. Great. And we know that for the integral test guys, all we need to do is to define some function such as f of x, which is equal to 1 over x raised to the power p. We are simply going to replace our n with x, and we define a function like I have here, f of x, which is equal to 1 over x raised to the power p. By this guys, what the integral test is simply telling us that this is the series that we have, the series as n goes from 1 to infinity of 1 over n raised to the power p guys. This our series, we have simply defined a function out of this such as f of x equals to 1 over x raised to the power p. Guys, the integral test is simply telling us that when we have the function defined in this form, if we take the definite integral going from 1 to infinity of f of x dx, so long as this guy gives us an answer, we can call that answer a. Now guys, if a is a finite number, namely from 0 to positive infinity, that is out of positive infinity, because positive infinity is not among, likewise negative infinity guys, so long as it gives us a finite value, then we can conclude that this our integral has converged, right? Namely, guys, the series as n goes from 1 to infinity for 1 over n raised to the power p has converged. Great. So it converges. Great. So guys, that is what we want to show. Okay, if you're able to get the integral of this guy from 1 to infinity, and we show that it gives us a finite value, then we can say that this our series has converged. Great. All right, guys, let's look at the integral from 1 to infinity of f of x, which is simply what, guys? 1 over x raised to the power p. We have dx. So guys, by our law of indices, we can express 1 over x raised to the power p as just the integral from 1 to infinity of x raised to the power negative p. As you all know, guys, this is a polynomial function of which we can just do the reverse power rule. That is, we add 1 to the power and divide by the new power. We are going to have 1 over 1 minus p times x raised to the power 1 minus p. The limits of integrations, guys, will be going from 1 and ending at infinitive. Great. So guys, that's what we have. In this case now, guys, we can plug in 1 in place of x, right? If we plug in 1, guys, 1 raised to the power 1 minus p simply gives us 1. Likewise, if we plug in 1, like I said, we are just going to have this part containing x giving us 1. So we are going to have 1 over 1 minus p. Now, guys, if we plug in infinity, we are simply taking the limit as our x goes to infinity of x raised to the power 1 minus p minus, when we substitute the lower limit, which is 1, we are going to have just 1 over 1 minus p. Great. So guys, this is what we have. We know that when n goes to infinity, guys, and the condition we took here that what p has to be greater than 1, right? So if p is greater than 1, that therefore implies, guys, we are definitely going to have the power that is 1 minus p simply doing what? It's simply less than 0, right? Because we said p is greater than 1, namely that is p can be 2, it can be 3, it can be whatever. If p is above 2, or if p is above 1, right, we can see that the power here is going to be what? Less than 0. Great. And guys, we'll also see that the limit as x goes to infinity of x raised to the power 1 minus p, since the power is less than 1, namely, guys, the power is negative, this our limit will simply die down to 0. And as such, guys, all we are going to see now is that the integral going from 1 to infinity now of f of x will just simply become what? 1 over p minus 1. We have simply taken the negative, we have simply factored the negative in the bottom here, and it cancels with the 1 we have. That's why we have a positive 1 over p minus 1. And guys, since our p now is greater than 1, this guy becomes positive, right? Great. That's just it. So now, guys, we can therefore say that 1 over p minus 1, guys, is a finite value, right? Since p runs from where, guys? Runs from 1 to positive infinitive. Great. So 1 over p minus 1 is a finite value. So this our integral now from 1 to infinity now of f of x dx has given us what? 1 over p minus 1, and it is what? A finite value. So we can say that in this case we have a convergent situation. That is a series as n goes from 1 to infinity of 1 over n raised to the power p does what, guys? Converges. Great. All right. So guys, this is a case where p is greater than 1. The series converge. All right. Now, guys, let's look at case 3 when p now is less than 1. If p is less than 1, guys, you can see that what the power in this case, right? The power in this case, that is 1 minus p, since p is less than 1, namely p can be 1/3, it can be 1/2, and so on, guys. That is improper fractions. It therefore means that is proper fractions, sorry, proper fractions. We are going to have 1 minus p being what? Less than being greater than 0, right? It therefore means that we are going to have 1 minus p to be greater than 0, and consequently, guys, if the power in this case, the power of this our limit is positive, right? It therefore means that what? This our limit, that is as x goes to infinity of x raised to the power 1 minus p, guys, is therefore going to give us what? Infinitive, because the power in this case is positive, and the limit in this case can never approach 0. It can never approach 0. It's going to go very, very big up to positive infinitive. Great. So, guys, when we have infinitive, right, it therefore means that what? Since our integral now, the primitive of our integral, that is without the limits of integration, guys, was 1 over 1 minus p, x raised to the power 1 minus p, right? The limit were from 1 to infinity. So when we plug in infinitive, guys, we are going to have infinitive minus, when we plug 1, we are going to have this finite value. But guys, infinity minus a finite value simply gives us what? Infinitive. So we can conclude that this our integral now from 1 to infinity of f of x dx when p is less than 1 diverges, right? Or it is going to give us what? Infinity. It therefore means that it has diverged. As such, guys, the original series, namely from 1 to infinity of 1 over n raised to the power p, now guys, diverges. So in this case, guys, we can simply draw our conclusions that the p series simply converges whenever p is greater than 1, and it diverges whenever p is less than or equal to 1. When p is equal to 1, the p series now becomes a famous harmonic series that we all know. Great. So guys, that's it for our video today. That's it, guys. If you love the video, please give it a thumbs up. That goes a long way, guys, to motivate me. It tells me that you found the content so useful, and I'm going to keep producing more great content for you guys. Thank you very much, and have a blessed day.